Now that we've finished talking about ANOVA tests and confidence intervals related to them and things like that, we're going to spend the rest of the semester focusing on relationships between quantitative variables. So we'll start out talking about how we can describe how two quantitative variables are related, and then hopefully by the end of the semester we'll actually extend this to more than two quantitative variables. But before we get too deep into our sort of main way of doing this, which is with something that we call linear regression, we're going to first talk about scatterplots, so how we might visualize this relationship, and then correlation, which is a single number which can help us describe the relationship between these two variables. So a scatterplot, you've almost certainly seen one of these before, even if you didn't necessarily know the name for it, is going to show this relationship for our two quantitative variables. And we're going to put one of those variables on the x-axis, we're going to put one of the variables on the y-axis, and then we're going to put a bunch of dots on the graph. And every dot is going to be a person or an observation, and we're going to be able to look at the graph to see what the x value was and what the y value was. And since we've got two different kinds of quantitative variables, we should think about which one might go on that x-axis and which one might go on that y-axis. And we have different names for these variables. So we refer to one variable as a predictor or an explanatory variable if it's used to help us explain what's happening with that other variable, or possibly to make a prediction for it. The response variable, then, is the thing that we're trying to predict. And it's called the response because you can think of it as responding to changes that you would make in your explanatory variable. So sort of a simple example, let's say I'm looking at how long someone studies for an exam and the score that they end up getting on it. You might want to use how long you study to help you predict your score on the exam. So the amount of time studying would be your explanatory variable. It's going to help explain how well you do. And we're hoping that your score on the exam will respond to changes in how long you study. So that would be your response variable. To actually get this scatter plot that we're talking about in SAS, we're going to use the SG-plot procedure. You've actually seen this way back at the beginning of the semester. Some of you used this for the Olympic swimming project, but you may not have used the scatter statement or scatter line. So if we want a scatter plot, we'll put the word scatter here on the second line under proc SG-plot. We'll put x equals the name of our explanatory variable, y equals the name of our response variable, semicolon at the end of that line, and then run. And I'll show you an example of this in just a second using this data set from the Challenger disaster. So this happened a long time ago at this point. It was in 1986, but the Space Shuttle Challenger launched, and upon launch it exploded over the Atlantic Ocean, and 7 astronauts ended up dying in it. And so this was a really important event because people wanted to prevent something like this from happening in the future. And they determined that they thought that this thing called an O-ring basically kind of broke down during the flight, and that's what led to the explosion. And there was a belief that this could be related to the temperature at launch. So it was around 0 degrees Celsius when the rocket launched. All right. So what we're going to do is we're going to look at the relationship between the temperature at launch and how much damage this O-ring takes on during the flight. All right. So one thing that we can do is we can go to this 18-Challenger dataset. So I'm going to go to SAS Studio here. You can see here's the dataset in our list of files. As a reminder, you'll go to My Shared File Links. You'll go to this U with a bunch of numbers, and I'll find 18-Challenger. I am going to copy this into a new file, because remember, if you try and edit the original file, you might get some errors and things like that. And if we look at the data, we've got two variables. They're both quantitative, the temperature at launch, and this is the damage index for the O-rings. And if you think, all right, which one of these are we trying to predict? Which one do we think helps us explain the other one? Well, they want to predict how much damage this O-ring is going to take. That's the important thing. They, want to launch the flights in situations where the O-ring is going to be fine. And it's believed that the temperature is going to help make that prediction. It's going to explain some of the changes that you'll see. So when we use proc-sgplot, our data set's called Challenger, so I put data equals Challenger. And then on the scatter line, I'm going to put x equals temp because I think this will help me explain the damage index. So y equals index. And if we run this code, we will get a graph here in just a second. And this graph is included in the notes as well. So I'm going to go back to the notes to look at this. So what do we notice here? One thing that you hopefully notice is that when the temperature is lower, that's when you tend to see higher damage indexes. When the temperature is higher, you've got a lot of times where you actually saw no damage, so an index of 0, but you tend to get lower numbers here at high temperatures. So it seems like low temperatures tend to be related to high damage indexes. The other thing that I would want you to pick up from this is that we said that their flight launched when it was 0 degrees Celsius out. Our data only goes down to 12 degrees Celsius. So we may have an idea that, yeah, generally low temperatures mean high damage index, but on top of that, we really don't know what's going to happen when the temperature is 0, because we haven't seen data sort of that shows us that. It's entirely possible that the relationship between 12 and 20 degrees is not the same as the relationship is around 0 degrees. So that's something that we should be a little bit careful about. So we're going to come back to this in a few minutes. But first I want to talk about what sort of features should we pick up on when we're looking at a scatter plot. So we can use a scatter plot to tell us three main things. We can look at what we call the form of the relationship. For our class, we're just going to focus on, is it linear? Does it look kind of like a straight line could be drawn through the picture? Or is it nonlinear? Is there some other kind of pattern there? We can also talk about the direction of the relationship. That can be positive, negative, or neither. We'll talk about what that means in just a minute. And we can talk about the strength of the relationship. Does it look like there's a really strong relationship between these variables? Or maybe there's some relationship, but it's kind of weak. There's not a whole lot going on there. So let's look at some examples for each of these. And we'll start with the form. I've got 3 graphs here, and I've drawn lines through them indicating sort of what I see as the pattern of the points. So for this graph, there's sort of this like curve here, and then it levels off, and then you have sort of this upward curve. For this graph, I could draw sort of a straight line that looks like it explains or describes the points fairly well. And then for this one, I've got sort of this parabola here. So the middle one, I would describe that scatter plot as having a linear form. It looks kind of like a straight line. Now, not every point is exactly on the line, but that's the general pattern that I'm seeing. Whereas these two on the left and on the right, those look nonlinear. There's some other pattern that I'm seeing there. All right, so that's how we can talk about the form of the scatter plot. What about the direction? The direction of the scatter plot is based on the slope of the line. So this may take you back to sort of previous math classes that you've taken, but a positive slope means the line is going up from left to right. A negative slope means the line is going down from left to right. And if it has no slope, or neither a positive or negative direction, maybe you would see something where the line's just like flat, for example. And so let's look at a couple more examples here. All right. On the left, I've got a negative slope. My line is going down from left to right. So if you looked at like the equation of this line, the slope would be a negative number. Another way to think of that is that high y values tend to go with low x values, and high x values tend to go with low y values. So we refer to that as a negative direction. The graph on the right here, I've got this line with an upward slope, so it goes up from left to right. That means that low x values tend to go with low y values, and high x values tend to go with high y values. The one in the middle, I might say, doesn't have a positive or a negative direction, because this part of the graph, it looks like there's a negative slope. This part, it looks like there's a positive slope. So I can't really say that high x values go with, high values, low y go with low, because there's sort of this mix going on. All right. So these are the types of things that we might pick up on for a scatter plot. If you're going through the notes on your own right now, I've got a couple examples where I want you to think about whether these pairs of quantitative variables would have a positive relationship, a negative relationship, or neither. So you can pause the video right now and do that, but I'm going to look at them here with you. Height of a mother and height of a daughter. We would expect that to have a positive relationship. Tall mothers tend to have tall daughters. Short mothers tend to have short daughters. And notice I'm saying tend because it's true that you're not guaranteed that you're going to be like the same height as your mother or anything like that. But this is sort of the general trend that we would see. For another example, the daily Dow Jones Industrial Average and the daily rainfall in Seattle. There's neither a positive or negative direction for that. It doesn't seem like these two variables would be related at all. If we made a scatter plot, you might imagine that it's just kind of a big blob of points with no real distinguishable pattern. Person's age and a person's birth year. This would have a negative relationship. If you imagine a newborn, they're going to have a high birth year, a big number, say 2020. An older person will have a large value for their age, but they would have a small value for their year. They would be born in 1930, for example. All right, so this graph would have a negative slope. The last one, the weight of a car and its mileage per gallon, we would also expect this to have a negative direction. Heavy cars are more likely to get worse gas mileage. Again, just like the mother's and daughter's heights, it's not guaranteed that if my car is heavier than your car, I'm going to get worse gas mileage, but that's the sort of general pattern. If a car is really heavy, it takes more power to make it move, and so it's probably not going to get as good of gas mileage. We will pick up part 2 of our video looking at the third characteristic, which is the strength of the relationship, and then we'll start to talk about how we can quantify some of these things so that you don't just have to sort of describe it in words. We want to be able to put numbers to a lot of this.